Okay, picking up where we left off last time, we were getting into kinetics and rates and other fun stuff like that. We learned a generic rate for chemical equations, and we can answer questions like this. The reaction A to B has been experimentally determined to be second order. The initial rate is given with an initial concentration of A equals 0.100 molar. What is the initial rate at this other concentration? One of the ways, the way that I am thinking of to solve this problem is we know that rate equals rate constant, concentration, in this case of A, raised to the n power, right? That's our normal rate law. And this n we've determined is 2. So raised to the second power. We are trying to find another rate, a second rate. To find that second rate, we need to know K and we need to know the concentration. We don't have K yet, but we can figure it out based on that first set of conditions that we were given. So 0.0100 molar per second equals K times 0.100 molar squared. We'll get the K by itself. And if I'm not crazy, that K is 1. If I am crazy, I'm not crazy. So that's very convenient. K is just 1 over molar seconds. So if we increase the initial rate to 5 times what it was before, rate is what we're finding. K is equal to 1 times 0.500 molar squared that'll be 0.250 molar per second. So that would give us D. We can also have situations where we've got different kind of weird reaction orders, like if we have multiple reactants. So we've been looking at with just one reactant, like decomposition reactions or something reacting with itself. But we can also have multiple reactants, and our rate law is going to look very similar. We just added a second term. But the form is the same. They just have different superscripts. And we can also get an overall order. And we're just adding the reactant orders. And we need to determine this by experiment, as with all of our rate laws. So for example, if m equals 2 and n also equals 2, the overall order is 4. We've added the 2 and the 2. If it was 2 and 1, the overall order would be 3. Some examples of that. We've got two different equations here, both with two reactants. We've determined the rate for each of them, and we've got the order for each of the reactants. We probably determined those separately. So for rate 1, one plus 1 equals 2, overall second order, or overall order of 2. For our second one, 1 and 2, we've got an overall order of 3. And the first one is, because we're also asked order with respect to each reactant, first order with respect to WRT, H2, also I2. The second one, first order with respect to WRT, H2. Second order with respect to no. Easy to read off. The harder part would be coming up with the individual order of the reactions. But we have the tools to do that. It's pretty similar to what we've done before, and we've got an example for that. The initial rate of reaction for this reaction is measured at several different concentrations of the reactants with the following results. In that table from the data, determine the rate law and also the rate constant K. The first thing that we're going to want to do is write out our rate law. So our rate is equal to K times the concentration of our first reactant raised to some power times the concentration of our second reactant raised to some power, possibly a different power. And there was a special equation sort of thing that we used last time that I showed a simplified version of. We're going to do the same sort of thing. So we're taking this rate law in one state. We're going to divide that from another state. So state 2 over state 1, or state 1 over state 2. 2 over 1 is easier. And we're going to do that because we've got data for each of these. Very conveniently, the way that we've done this experiment, we've got a set where we're doubling the concentration for our CHCl3, but we're not changing the concentration for our chlorine. And then we hold the CHCl3 constant at 0.02, and we double the concentration of the Cl2. So that lets us isolate the effect of each of these changes from the other. And we've got rates for both of those. Do these in different colors. So we'll have rate the second over rate the first equals K2 over K1 CHCl3 concentration raised to the m power, that's the second state, CHCl3 concentration raised to the m power in the first state, and also Cl2 raised to the n power in the second state, Cl2 raised to the n power from the first state. So what's convenient about changing one of these variables at a time is that when we're changing the CHCl3 concentration, our Cl2 concentration is the same in both sets. So we're having the same concentration. They're going to have the same order. So Cl22 over with the n power, those will cancel out. So all these over on the right side, those cancel out. The K2 over K1, the rate constant, hasn't changed. So that also cancels out. So we can simplify this down to rate 2 over rate 1 equals, for the red set, concentration CHCl3 second state raised to the m power CHCl3 in the first state, also raised to the m power. We pull out the m power. And this was sort of that condensed, that simpler form that I showed you. And then all we have to do is plug in values. If you're sort of quick with rough approximations or some math, 0.02 over 0.01, we've doubled it, right? Double the concentration, 0.0069, 0.0035, we've about doubled it. I'm going to say that's close enough that it's probably just an experimental error. So this turns into 2 equals 2 raised to the m power. What do we think m is? M is 1. So we've determined that this reaction is first order with respect to CHCl3.
Why didn't our CHCl3 cancel out? Where our CL2 cancel out our case?
So the CL2s are the same for this set. We're looking at this red set, right? 0.01, 0.01. So that's why I was able to cancel those out. These other ones didn't cancel out because they're different. The Ks were also the same, so we canceled those out. So then we do the same process, same concept for Cl2. This time we've still doubled our concentration of Cl2. So the right side is going to be 2 raised to the n power. The left side, we did not double, 0.0098 divided by 0.0069. Our rate went up by 1.42 and some other stuff. So it's not going to be 1 because it went down a little bit. It's not going to be 2, so it will have to be something smaller than 1. Any ideas about an exponent smaller than 1? If it was 0, then this would have turned into a 1. So we can try fractions. So if we had n as 1/2, that would be a square root. So you can plug in square root of 2, start there. And my calculator decided that it did not want to tell me what that number was. But that should be the correct one. You could also do a cube root if that didn't work out quite right, or a quartic root. In this case, n works out to be 2. 1/2, sorry. So it's 1/2 order with respect to Cl2. And then to find K, you just plug in any set of these conditions. Doesn't matter which one you choose, and solve for the K. I ran out of room, and I'm trusting that you can also do that. So
With using the M and the N?
yeah, plug in the M and the N values that you got.
So just using the green formula, we can figure out K, right?
Correct, that green formula. Questions? Golden. This reaction was experimentally determined to be first order with respect to O2 and second order with respect to NO. The diagrams shown here represent reaction mixtures in which the number of each type of molecule represents its relative initial concentrations. Which mixture would have the fastest initial rate? The three situations that we've got are an even number. We've got 3 NOs and 3 O2s. We've also got a situation where we've got 4 O2s and 2 NOs. And we've got this last situation where we've got 4 NOs and 2 O2s. Which of the reactants is going to have the biggest effect on our rate? The bigger effect on our rate? The NO. Why is the NO going to have a bigger effect? Because it's second order. First order with respect to O2, second order with respect to NO. If you wanted to, you could plug these in. Make up some numbers. You could just use the whole numbers here. That would probably work. And just make up that K is equal to 1 and see which one has the fastest rate. If I'm not crazy, should be C.
Because it's second order, it affects the rate more?
Yeah, because it's second order. If they were both first order, then you might want state A where they're even amounts. That might end up being the fastest. All right, we've looked at the relationship between rate of reaction and concentration of a reactant. We'll see those again in a couple slides. The integrated rate law, integrated like from calculus, gives the relationship between concentration and time. And it allows us to predict, which is very helpful, the concentration of reactants or products at a future time, which we haven't been able to do before. And the version of the integrated rate law that we use depends on the order of the reaction. For us, that's going to be 0, 1, or 2 for the order. You might be thinking to yourself, there's already so many equations that we've looked at that are all kind of similar. That's going to be really rough to have to memorize all of them. So what I'm anticipating, since we're learning even more things, is I'm going to give you all of the equations. I won't necessarily give you the name of what the equation is, so you'll have to identify based on the type of equation that it is, what it does and which ones to use. So it would still be a good idea to practice, like with flashcards or something. One side, this is the first order integrated rate law, and then the thing on the other side. Or make a chart, a study guide with all of these things laid out. There's actually a slide that will come up on that has all of them laid out at once, just so that you know which one to use. And then also with the homework, you'll get practice using them, so hopefully you know how to use them once you've identified them. For our first order integrated rate law, for a simple decomposition, so just one reactant, that's what we'll be looking at. For our A going to products, the rate is equal to K times A. Our little exponent there is 1. And our rate is also equal to the negative change in the concentration of A over change in time. And since these are both equal to rate, we can make them equal to each other. And we can call this the differential rate law. So at one period of time, or comparing 2 points in time, we can figure out what our rate is at that moment or between those 2 moments. And then after we do some calculus, which you don't need to know how to do the calculus, there's videos on it online on YouTube, and some rearrangement, you end up with the first order integrated rate law, which has these 2 forms. They're the same thing, it's just that one of them's been rearranged. So the natural log, ln, of A at some concentration of A at some time is equal to negative K, the negative of the rate constant, times the time that we're at. Those T's are linked. Plus the natural log of the initial concentration of A. So that A naught, that's the initial concentration when time is equal to 0. And you might notice that this left form looks kind of like y equals mx plus b. Sort of has that same shape to it. And that's what we're taking advantage of in this plot. So our x here is time. So we put time on the x-axis. And what is in the spot where y would normally be, that ln concentration of A at time t, that's our dependent variable, our y-axis. So if we plot these against each other, then we'll get a straight line, because it's a linear equation. And for that line, the natural log of our initial concentration is where our b would normally be. Our y-intercept. And then the slope of the line is negative k. So that's a cool application of the first order integrated rate law, is that you can make a plot like this. You can also collect data and then plot it like this. If you have concentration data and time data, you can make one of these plots. If you get a straight line or a roughly straight line, then that's a good indication that you have a first order reaction. So that's neat. And here's what that graphical analysis might look like. This is an example. You don't have to do this calculation because that's a lot of data. So this is that thing I was talking about. This concentration of our reactant was monitored at a fixed temperature. So our rate constant is constant. And as a function of time, during the decomposition reaction, and the following data were tabulated, show that the reaction is first order and determine the rate constant. So the way that I would do this is I would take all this data, plug it into Excel. So all my time data, that's my x's. And then all the concentration data, you can have Excel do the natural log function. It'll spit that out, plot those things together. You could also do this on a graphing calculator. And you would get a plot that looks like this. So our x-axis, again, we have time. On our y-axis, we've got the thing that showed up in our y spot, our y position, the natural log of our concentration. And we can see that we got really good linear data. And if you do it in Excel, you can have it spit out a regression, a linear regression for you. And that kind of just gives you your rate constant and other information. So what is our rate constant here?
Do you know how to find it, or is it just the slope?
It's related to the slope. Yeah, so it's just the negative of the slope. Our rate constant is always going to be positive, so we'll just use the positive version.
So if we find the slope, it's just whatever the slope is with the positive is going to be the rate constant.
For this, yes.
It's always going to be positive, right? If it's negative, the constant.
Yes. And then what are our units for the rate constant for a first order reaction? We can write out our this thing, right? That's our first order differential rate law. Rate equals K times concentration of S. Our rate is always going to have units of molar per second. We get our molar from the concentration, so our K has to have inverse seconds for the rate constant. Sort of just a pop quiz that I thought I'd throw in there for you. Another thing that we can do with this, we can use the graph in the best fitting line, that linear regression line, to predict the concentration at 1900 seconds. For this, it might be helpful, well, it's definitely helpful to remember what parts of this equation are at least, but we can actually get it from the graph as well. What are we graphing on y, our y-axis? What's the label for our y-axis? The vertical one. Y is that label, the natural log of the concentration. So we can plug that in for the y in this linear regression. Not equals minus 2.30. And now if we want to find the concentration of the SO2Cl2 at some time, we just plug in whatever time we want to this equation. It'll spit out natural log of the concentration, and then we can convert that to just concentration. Is that making sense?
Do we have to label it as the Ln concentration of that, or no? Can we do that as y?
You can leave it as y. You'll just have to remember that it is
The concentration.
natural log the concentration. If you don't do that, you'll get the wrong answer.
Does it still have to apply the natural log after? To the concentration?
You have to undo the natural log.
Undo it. Okay.
Yeah. So what I'm going to do is plug in that 1900 seconds. And I'll do that in red since I've written everything in green. And then we can evaluate what the right side of the equation is equal to here. So minus 0.00029 times 1900 minus 2.3. For the right side, I'm getting minus 2.851. The left side is still the natural log of the concentration. Does anyone remember how to undo a natural log? Yeah, we do the e to the power for both sides. So e raised to the power of the natural log of the concentration, those cancel out. And our concentration is going to be e raised to the minus 2.851. And its concentration, so it'll be molar for units. So 0.0578 molar, something like that. Questions?
So to get rid of the natural log, you put e to that natural log, or?
Yeah. Talking about logs always seems to melt my brain in a special way. But yeah, you just raise both sides to the base of whatever the log is. So normally if it's just log, we would do 10 raised to the power of both sides. That undoes the log. The ln is just log base e. So instead of doing log base 10, e. So we raise both sides above an e to undo it. I'm sure there's a better way to explain that, like in really good, solid math terms, but I'm not a math person by training. All right. Cyclopropane rearranges to form propene in the gas phase. The reaction is first order in cyclopropane, or with respect to cyclopropane, and has a measured rate constant of 3.36 times 10 to the minus 5 inverse seconds at a temperature. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235 minutes? I'll give you a couple minutes to try to figure it out, and then we'll come back and solve it together. All right, how we doing? Looks like people are making some progress. So the equation that we're going to use, you can use either of them, but I'm going to use the same one that we were just using. So that's this natural log concentration of whatever our thing is, cyclopropane. Again, if I'm not crazy, C3H6 equals negative KT plus natural log, forgot a T label for that first concentration, natural log of this C3H6. We were given a bunch of stuff. It's crucial that it's first order because we don't know our other integrated rate laws. And we've got a rate constant that's given to us. That's our K. The at 720 Kelvin, it's not particularly important for us here. That's just to let us know that it's at a specific specific temperature. We've got an initial cyclopropane concentration. That's our concentration with that 0 subscript. And we want to find the concentration at a time of 235 minutes. Can we plug everything in and just solve it right away? We cannot. The reason that we can't do that is because we were given a time in minutes and our rate constant is inverse seconds. So we need to make sure that we switch from minutes to seconds. So multiply by 60. Our time is 10:15. But the time in the problem is 14,100 seconds. It's a dumb joke. Okay, now that we've got our things, we've got K, we were given K. We've got T, we just figured it out in seconds. We've got an initial concentration. We can evaluate the right side of the equation, do the E to the both sides thing, and that'll give us our concentration. If you wanted to, you could raise both sides as the power of E before, and it'll just mean a more complicated thing to put into your calculator. That's fine too. Okay, so this equals minus K times time plus natural log of 0.0445 molar oh no. Okay, just moving some stuff around there. So plug that into your calculator. I'm getting out minus 3.586 dot 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 with units, whatever those might be. I'm not going to worry about you keeping track of what happens to your units when you're putting them through a natural log function, because we know that we're getting out concentration and it's going to be molar. So that's where we are, and we can do our little e trick. E raised to the minus 3.586 dot dot dot, and that will have units of molar. So our concentration at 235 minutes is 0.0277-ish molar. Fun stuff. All right, we also have second order integrated rate law. For this rate law, the thing that's different is, well, it's second order. And again, that's our differential rate law. This is stuff that we've seen before. So whammo blammo, we do calculus and integrate it. And it will also come out in a form that we can turn it into what looks like a straight line. Right, this has the form of y equals mx plus b. Time is still just time. Our y, instead of natural log of the concentration at some given time, is now 1 over the concentration at some given time. So if we do a plot of what we have here as x and y, the time and 1 over the concentration at a given time, we still get our y-intercept out, something that we could turn into our initial concentration, and this time our slope is positive k. You may be asked to identify if something's if it's 0, first, or second order based on a plot with axes given. Yeah?
0 is just a straight line, right? Like a flat one?
I think we're going to see that in a couple slides. We'll see the 0 order. So notably, this is a different y-axis. We can also do graphical analysis of reaction data for something that's second order. Obviously, this would take you a while to plug in, especially if it was on a calculator. And this is just an example, so we'll see it plotted out. The important things are here that we're trying to show that it's not first order and that it is second order. So we would want to do a first order plot where y is the natural log of the concentration. So all of these data points, the 20 or some that there are there, natural log of all those, plug those in as our y values against time, see if it's a straight line. If it is, then it's first order, or we do the 1 over that, like we saw previously, to see if it's second order, and then we can determine the rate constant. Here's what that looks like. So we've got our first order plot. We've got our second order plot. It is not along this straight line. We've got a regression line there still, but it's not holding very tightly to those points. You can see that there's a little bit of a curve to it. So that's a sign that it's probably not first order, and it fits our second order plot very, very nicely. It runs perfectly through that data. And so this is second order. And where do we find our rate constant? Our rate constant is that 0.255. For the second order plot, it's positive, so we don't have to flip it. So that's a convenient similarity between our first and second order plots. Our k is in the same location. We can also use the graph and the best fitting line to predict the concentration, just like we did before. We're going to do the same little trick. So we've got our regression line that's given to us. We're trying to find a concentration at a given time, 2,000 seconds. What is y on this plot? It's 1 over the concentration of NO2. And the rest of the equation is this 0.255x, which we know is time, plus 100. So plug in 2,000 seconds for time, and we can evaluate the right side. This comes out as 610. And our left side is still 1 over the concentration of NO2. So we'll inverse both sides. Which transforms this into a concentration of NO2, which is equal to 1 over 610. This will have units of molarity. Question?
So if you just use that formula instead of the one we did for this, this isn't a second order integrated law?
This is a second order integrated rate law.
So we wouldn't use the other formula, or we would? The one we used before?
So the second order law thing that we were looking at,
That one, yeah.
this one, the K has already been solved for us. It's in our equation. And the 1 over the initial concentration, that has already been calculated out. So if we wanted to find our initial concentration, then we would have to do a transformation to what we had for 100, that B. We don't need that number, and so we'll just plug it in. I actually did the same thing when I was reviewing the slides last night. I was like, why am I getting the wrong answer? And it's because I had that flipped. Okay, so 1 over 610. This gives us a concentration of, we'll do it in scientific notation, 1.64 times 10 to the minus 3 molar. We also have a 0 order integrated rate law. When it's 0 order, remember that the concentration of A factor disappears for our rate law. And so we have a simpler starting rate law, differential rate law. We integrate that and get this. So that's our zero order integrated rate law. We can plot concentration over time as our y-axis, and we will again get a straight line with the slope being related to k. In this case, it's negative again. And our y-intercept is our initial concentration.
So this one just doesn't have the L in it.
Right. No natural log, no inverse. And we can do all the same stuff that we've been doing with this. I'm trusting that you're capable of doing that if you've been following along. Other stuff that we can do with our kinetics things is half-life. You may remember, if you took 3A with me, we got to radioactivity, we talked about nuclear half-life, and it was like, we can assess like in between half-lives. We can do that, but we're not going to do that for this class. And now we're in the class that we get to do that. So we can assess concentrations in between half-lives, thanks to our friends, the first, zero, and second order integrated rate laws. So as a reminder, the half-life, or T sub 1/2, is the time needed to cut the initial concentration to 1/2. So if our initial concentration is 0.50 molar and our half-life is 50 seconds, what is the concentration going to be after 50 seconds? Yeah, it'll be 0.25. So 1 T sub 1/2, or 1 half-life, has passed. So concentration equals 0.50 molar divided by 2, which is 0.25 molar. That's for 50 seconds. For 100 seconds, 2 half-lives have passed. And some people think, okay, well, we cut it in half every half-life, so we lose half of our initial amount again. That means we have 0, which is not how it works. We're cutting it in half for every sequential half-life. So we're going to cut it in half 2 times. We put 2 2s in the bottom. 0.125 molar. We cut it in half again. We also, as I alluded to, we've got different integrated rate laws that we're getting to use for this. It's different depending on our reaction order. So we'll look at all 3 of those cases coming up. Questions about half-life before we get to the integrated rate law stuff?
If 2 half-lives are just fast, can we not just go 0.25 divided by 2 again?
You can also do that. It's the same thing, yeah. So you can divide the, after 1 half-life, divide it again. If you have a bunch of half-lives and you want to do 2 raised to the power of however many half-lives in the denominator, that also works. Or if you just want to keep track of how many times you pressed enter on your calculator when you divide by 2, that also works. They're all equivalent. All right, our first order reaction half-life. Our integrated rate law, this is the other form, not the one that we were using before. When time is equal to T 1/2, we know this about our equation, that the concentration is going to be 1/2 of our initial concentration. So what we can do is sub in this 1/2 bit, and this will turn into processing. Okay, here we go. You don't need to know how to do this, by the way. It's not strictly necessary. So the left side would turn into that, and that's equal to minus KT. And we do some fun rearrangement. And what's the fun that comes out? T equal to natural log of 0.5 over K. Trust me, the rearrangement is fun. And I believe that's correct. We'll find out. Look at that. T1/2 equals 0.693 over K. We might still have the negative there, but the long and short of it is that we get this. We do still have the negative there. Okay. The 0.693 is really fun and all. I think it's helpful to remember that it's got a natural log of 2 or natural log of 0.5. I think that's nice. So you can also do that. But you should recognize that the 0.693 is related to the natural log of 1/2. So for our first order reactions, our half-life is independent of initial concentration. The T1/2 is our half-life, and all that it depends on is our rate constant. So it'll be the same half-life every single time. So after one half-life, we cut the concentration in half. After another half-life, which is the same half-life, we cut it in half again. After the third half-life, we cut it in half again, and so on and so forth. So that would be the equation to put on a flashcard if you want to memorize or work on your identification of these equations. We've got some images that depict first order reaction A to B at various times. The black circles are A, the red circles are B. What is the half-life of the reaction? Any ideas? 90 seconds. We figure out that it's C, or 90 seconds, because our initial concentration is 10. We've got 10 dots. And we're looking for when that number has cut in half to 5 dots. Which is that fourth frame, or C, 90 seconds. For this one, you don't need a calculator. You can use a calculator if you really want to, but you don't. A first order reaction, A goes to B, has a half-life of 25 minutes. If the initial concentration of A is 0.300 molar, what is the concentration of B after 50 minutes? The important information that we want to pull out is our half-life, T1/2, is 25 minutes. Our reaction is A to B. Our initial concentration of A was given, and we're looking for the concentration of B after 50 minutes. 50 minutes is 2 half-lives. So what we've been doing so far is calculating concentration changes for A. The concentration change for A is going to result in the production of B. So A breaks down, goes through 2 half-lives. So our concentration of A at 50 minutes is going to be our initial concentration over 2 to the second power, 2 half-lives passed. .075 molar. We cut it down to 0.150. We cut that in half, 0.075. So that's the amount of A that we have. We lost how much A? 0.225, the 0.300 minus the 0.075. So that must have turned into B. So B is the correct answer. Continuing to chug along, a first order reaction has a half-life of 26.4 seconds. How long does it take for that to drop to 1/8 of its initial value? Who's got it? Sounds good to me. So we got 79.2 seconds. The way to solve this problem, we're given a couple pieces of information. We're given our half-life, and we're given that it falls to 1/8 of its initial value. So we've cut it in half a number of times until it gets to 1/8. Which means that we've cut it in half. 3 times 8 is 2 cubed, or 2 to the third power, so 3 half-lives. So 3 times 26.4 seconds is 79.2 seconds for our answer. So that's our first order half-life. For second order reaction half-life, we've got this. And again, we know this one simple truth. After a half-life, our initial amount has been cut in half. It's kind of definitional. And so we're going to plug that in. Again, you don't need to know how to do this. So 1 over 1/2 the initial concentration equals kT plus 1 over the initial concentration. We can turn this left side, that 2 can flip up to the top. So 2 over the initial concentration. And we need to move, or we want to move that 1 over concentration A naught to the left side. That leaves us with kT on the right side. These have a common denominator, so we can combine them. So that becomes 2 minus 1 over concentration of A naught, which of course turns into 1 over A naught, and that's equal to KT. If I did that right, that's what we see here. It is what we see here. We just divided both sides by K. So that's nice. That's how we get there. You don't have to know how to get there. You just need to know how to use the equation. I just think it's fun to show you. So this, notably, has the initial concentration in the denominator. A lower initial concentration a smaller A naught increases T1/2. And the half-life also gets longer as the reaction proceeds. So these are both great facts to know about second-order reaction half-life. On the other hand, if you have a high initial concentration, a bigger number in the denominator, this A naught, a bigger number there makes your T1/2 smaller. That's all that first point is, looking at the relationship between those two. For our zero-order reaction half-life, we've got this. We do the same old song and dance. We get that. We move this concentration of A naught to the left side. That equals negative K T1/2. We can give those a common denominator so that we can subtract them. So this left side turns into minus concentration of A naught over 2 equals minus K T1/2. We do some stuff, divide both sides by negative K, and we get concentration of A naught over 2K. Hopefully that's correct. Look at that. We did it. We did it, chat. So there's our zero-order reaction half-life. Notice that this also has the concentration of A naught in it. This time it's in the numerator instead of the denominator. So half-life for this also depends on the initial concentration, but it's the opposite. The half-life gets shorter as the initial concentration decreases. So these are directly proportional or directly related. And the half-life gets shorter as the reaction proceeds. Another way that you can think about this is a zero-order reaction has the same rate the whole time. It just depends on the rate constant. So if it has the same rate the whole time, you're using up fuel at the same rate. As you start to cut your amount down, it takes less time for it to cut in half. That makes sense in my brain. If it didn't land for you, that's no big deal. So those are some good things to know about zero-order reaction half-life. And here's that fun table that I was telling you about. So this has our order, It's got our rate law, units of k, which you could come up with on your own, integrated rate law. It's got the different straight line plots with all the y-axes labeled. And we have our half-life expressions. So you should be able to recognize what each of these is. You might have to use the straight line plot to identify which of the equations you use. But I'm anticipating, I'm planning to just give you all of the equations, probably not labeled. Questions? Okay.